Okay. So the practice 5.4, guys, that also came with an online 5.4. I haven't pulled that in. It's going to say overdoing your big ideas. I haven't pulled that in. So try to get that done by Monday also. Okay, so you might have to go in and check. I would encourage you guys 2 things. Check to see if that big ideas assignment 5.4 is done and submitted. That's 1. 2, also check JMC because that's completely up to date. So it'll tell you anything that you're missing. Was there a quiz not too long ago?
Yeah.
I told you there was a certain makeup date. Okay. There's a quiz in there. I think it was 5.1 through 5.4 that we did. Maybe it was 5.3. Thanks, buddy.
5.3.
The what was? Filter?
The one by the bedroom's always on red, and I'm just like,
Thank you. Let's just plan the next Friday. Have corrections on that. Okay. There was a quiz 5.1 through 5.3. I can't remember. It was like 16 points, wasn't it?
not one of us.
Can I see that real quickly, Maddie? This is the one. Okay. This is the one. And I would encourage you, if you're not sure about what you did wrong on that, I would strongly encourage you next week during win time, if you want to come in and discuss anything you missed with me, I highly encourage you to come in and talk to me about that, okay?
I should have selected then.
Okay. Still not too late. I mean,
But I already selected something else.
that's up to you. Totally up to you. Sure, absolutely. Absolutely.
It's 9:30. Can I still edit my response?
Maybe. I don't know. If you can always come down here and I can put you in if you want me to.
Can you put me in?
I can, yeah.
Okay, I'll select
Who are you
you.
going to?
I was just going to go to study hall. But
Okay, well, what I'll do is I'll have you report to study hall with a pass and tell you you're coming here, and then I'll get it in attendance, okay?
I think I got it in.
Okay,
I just didn't.
all right, sounds good. And I can check on my end at the end of the hour, all right? So, what we want to start doing today, kids, is this. Up here on the board on the left here, we have the condensed form of logarithmic functions on the left. We have expanded form over here on the right. And what we want to do is we want to take these ideas today, and we're going to use them to solve exponential and logarithmic equations. Volunteer for a central question. What are we trying to answer today?
How do you solve exponential and log?
How do you do it? How do you solve exponentials and logarithmic equations? So, to answer that right here, here's what we need to be able to do. I need to know how to solve exponential equations. I need to learn how to solve logarithmic equations. And then I also want to solve exponential and logarithmic inequalities. A little bit different. Okay? All right, guys, exponential equations. First one up there. These are going to be equations in which variable expressions occur as what? As an example, you might have 7. Whoops, I didn't want to do that. You might have an example like 7 to the x plus 3 power equals, I don't know, 28. Okay? When I say that this is an exponential equation, we say it's an exponential equation because my variable is a what? It's an exponent right there. Okay? So that's an example of an exponential equation. Anytime we need to solve that, we need, how do you find the x value? Now, very important, you guys have your calculators today because you're going to need them. Right? Then, logarithmic equations. Kind of the same thing. They're going to be equations in which the variables occur as not exponents, but variables are logs. Okay, the variables are going to be logs there. So to give you an example of what a logarithmic equation looks like, I don't know. How about something like this? I want to condense this a little bit. Variables are logs. An example of a logarithmic equation might look like this. Whoops. What's going on here? Variables are logs. Here's an example. Maybe log of x plus 7 equals log maybe 2x plus 4. The question becomes, how in the world am I going to solve those? Okay, so we'll look at stuff like this today. And it's not too bad, honestly. Not too bad. All right, extraneous solutions. We've talked about this before. Anybody recall what an extraneous solution is? Sometimes we get answers for equations that we work with. And when we take those answers and put them back into the equation, it can give us a true statement, or it can give us an extraneous solution, which is false. So sometimes we find numbers. So extraneous solutions are going to be what we consider, I just like to write it this way, they're false solutions, okay? Sometimes when we go through all the algebra and follow all the algebraic rules that we're using to solve equations, sometimes when we get those answers, we have to take them and plug them back into the original equation to see if they even work. And sometimes the answers that we get will not work in the original problem. And if they don't work, we call them what type of solutions again? Extraneous solutions. I just like to say, nope, that's not working as an answer when we plug it back in. Okay? Okay. Inequalities. You guys know what inequalities are, right? Inequality, like x is greater than 4, or x is less than or equal to -2. You guys have seen inequalities before. I don't need to talk about that. Okay. Guys, I can make life really easy, or I can make life really rough for you. What would you like to do? Okay, I'm going to show you what rough looks like because it's got a lot to do with number sense, but then I'm going to show you the easy way. Is that fair? You guys okay with that? Okay. First example I have up there, kids. We're solving what type of equations? Well, example 1 says to solve what? Okay, exponential equations. Now, I can, again, like I said, make this very easy, or I can make this very difficult. Make it very easy? Okay. I'm going to show you 2 different ways. You guys decide what you want to do. All right? First equation I'm looking at is 81 to the x power equals 1/9 to the... Okay, let's think about this, kids. 81 and 1/9. 81 and 1/9. What's a common base for 81 and 1/9? 9 is, right? Okay? Now that's hard sometimes for kids to think about. What's the common base? But sometimes up here when you're solving problems, think this way. Think common base. All right? Sometimes you need to think common base. And a common base for 81 and 1/9 is what again? 9. Okay, we can write those numbers as a base of 9. Nine to what power would make 81, kids? 9 to the second. So one way of doing this would be this. Let's split this. This is really 9 to the second to the x power, isn't it? Ew. 1/9. Like 1 over 9. Or 1 over 9 to the first. Isn't 1/9 the same as 9 to what power? Negative first, okay? This is going to equal 9 to the negative first, all to what, kids? X plus what? You guys get the 9 to the second part up there. Because 9 to the second is what? Okay. Well, here's the deal, kids. When you've got like bases like this, if these are going to be equal, if you have like bases like this, 9, then that means that 2x has to equal your other exponent. Now I need to take -1 times what here, kids? 9 to the -1 is the 1/9 part, but that's all raised to what power? So this is going to become negative x minus 3 right here because I need to take negative 1 times that x plus 3 up there. Oh my gosh, Parson, what are you doing to us? I don't know. It's kind of difficult, right? All right, what do you want to do to solve this? Add the x to those sides. Okay, so do that. So this becomes 3x equals what, kiddos? Negative 3. When I divide, what's my solution? Your x value is negative 1 in that, okay? Sometimes when you have exponential equations, your job is to say, okay, look at the left side and look at the right side. The values that are not exponents, the bases in other words. Can you rewrite the bases as a common base? We had 81 and 1/9. Now, are you always going to be able to write stuff as a common base? No, you are not, okay? You will never be able to write everything as a common base. Some of it, yeah. I'm going to come back to that here in a second. What about this one here, though, where there is no common? 3 and 8. 3 and 8. Let's see. Is there a common base that we can think of for 3 and 8? Okay, well, but we don't want to go up. We actually want to go down. Can you think of some number that multiplies up to 3 and also multiplies up to 8? I can't think of it. 1 does. We don't want to use 1, though. Actually, 1 would stay 1, wouldn't it? 81 and 1/9 were easy to think about because 9 popped into our head, right? Now, some of you are like, oh, I don't know. The only factors of 3 are what? 1 and what? 3. What are the factors of 8? 1, 2, 4, 8. Let's see. Besides 1, are there any common factors between 3 and 8? Here's how you do this, okay? Think common base. That's the first thing I'm going to tell you. That's the hard part. You guys want the easy part?
No.
To solve exponential equations, use logs. Okay? Use logs. And here's how this is going to work. Okay? Anytime you have an exponential equation like this, we can use logarithms to undo that. Logarithms are like the inverse of exponentials. Here's what I do. I'm going to log both sides of this. This is how it works. If I have 3 to the x is equal to 8, let's think about this. What's 3 to the first power? 3 to the first power would be 3. What's 3 to the second power? 9. So think of it this way. Kids, over here on the left, 3 to the first is equal to 3. 3 to the second is equal to 9. We want it to equal what value? So my answer has to be somewhere between what and what here?
1 and 2.
1 and 2. When I say 3 to the x has got to be somewhere between 1 and 2 there, doesn't it? Here's how it works. Exponentials basically say I can log both sides. This becomes the log of 3 to the x equals, if I log the left side of the equation, I better darn well do what? Log the other side. Log of 8. Now, this is where all of your expanding and condensing formulas are going to come into play from last section. Take a look at the left side where it says log of 3 to the x. How would you expand that? What could I do with the x? Put it out front. So x times the log of 3 would equal what, kids? Okay, now I want you to start thinking this way. And I want you to ingrain this in your brain right now. When I start talking about logs, particularly logs of numbers, like log of 8, or log of 95, or log of 97, those are numbers. I have no idea what those numbers are. The calculator's going to tell you that. But those are numbers. This is kind of like saying the same as 3x is equal to 8. But instead of having nice whole numbers in front, have the log of 3 times what, kids? How could I get x alone at this point? Knowing that the log of 8 and the log of 3 are some number. Divide by what? My answer here, kids, is going to be the log of 8 divided by what? What'd punch it in. Log 8 divided by log 3. Better darn well be between what two values?
I was close. Can I do it? 1.8.
And I think we'll go two places on everything. Are you guys fair with that? When you get your big ideas assignment, it'll tell you how to round. Okay, but I'm going to go two places and notes. Are you fair with that? Where do we think that this was going to end up between? So we could have said x equals 1.89, is that right? Okay, I want to go back to something real quickly. I want to go back to rules. If I have 3 to the x equals 8, kids, this is the same as log base what, kids? 3 of what? Equals x. Real quickly, change of base formula says x is equal to log base 3 of 8. If I wanted to evaluate this, wouldn't this be the log of 8 divided by the log of 3? Isn't that what we ended up doing here? Log of 8 divided by log of 3 to solve for x? That would have been another way to do it. Okay? I want to go back to this first one over here. You don't need to write this down, but if you want to put it in here, I'm okay with that. I'm going to do the work over here on the board. We knew the answer to number, or the first one was going to be what, kids? What if I didn't think of a common base? I could have logged both sides of this, right? I could have said the log of 81 to the x equals what, kids? Well, you would have said log 1/9 parson to the x plus 3, right? Where do these exponents move, kids? Out front. So this becomes x log 81 equals, where's the x plus 3 moving to, kids? So this would have been x. Oh my goodness, this is going to be so fun. This is going to be x plus 3 log 1/9. See where I'm going with this? Now, again, this is going to get a little complicated. On the left, you have x log 81. We have to distribute here, so we're going to have x log 1/9 plus 3 log 1/9. Oh my gosh, Parson, how do you do this? I don't know. I want to show you something. You don't need to write this down if you don't want to, because we're going to look at more examples. Okay? Kids, how many of these terms have an x in them? 2 of them, right? And we're going to talk about this as we progress, but anytime you have logarithmic functions with a variable up front, get all the x's to the same side. So I want this on the same side as this. Okay? So this is going to be x log 81 minus x log 1/9. And that's going to equal 3 times the log of 1/9. I better make some room here, eh? Now don't check out on me. Hang in there with me. Hey, quick question. Remember factoring? Okay. What can I factor out of both of these right here? This would become x times the log of 81 minus the log of 1/9 equals 3 times the log of 1/9. All right, stay with me. When I have subtraction like this right here, I could write this as a single log by taking what divided by what? And when you divide by 1/9, isn't that the same as multiplying by the reciprocal 9? Somebody take 81 times 9 for me. 729?
Yeah.
Where can I move the 3 here? Okay. Or if you didn't move it, that's fine. I mean, but I'm going to move it up there. So this becomes a log of, what's 1 to the 3rd power, kids? 1. What's 9 to the 3rd power? Somebody punch that. 9 times 9 times 9. Is it 729? I think it is.
Yeah.
Okay, what I want you to do is this, kids. Okay, now I have a mess up here, and this gets really elongated here. How could you solve for x now? Okay, you're going to put this in parentheses first, divided by tell me what you get there. So you're going to go log 1 over 729 parentheses divided by log 729. Isn't that what we got over here? Okay, now, was there a lot of work up there? Absolutely. Okay? And using logarithms is always going to work, but if you can think common bases, does that make your work a little shorter here? This is hard for kids. This is hard for kids to think common bases. But if you don't have common bases, you can always use what here? P.
I still have a question. Like, how come the 9 disappeared and it went to 2x?
Because if I have 9 to some power is equal to 9, that same base to the other power, that means this power has to equal this power. If this was 9 to the 7th equals 9 to the something, this would have to be 7 up here, right? This exponent has to equal this exponent if you have, like, bases right here. It's like saying this. If I add cat to the 12x equals cat to the 4x plus 6, well, the bases are the same, right? So if I want these to equal each other, this exponent better be the same as that exponent, right? So I can simply say 12x has to equal what? If you can establish like bases like this, then you just take the exponents and work with them, okay? But here's the problem. Like we said over here, there is no common base for 3 and 8. Make sense?
Yes.
And I think that as we move through stuff here more, P, you'll see that, okay? So give me a little bit of time, and I think that as we go through this, I'll answer your question. So if that question's still in the back of your mind at the end of this, let me know, okay? All right, let's move. Next page, kids. Let's see where we're at here. Gosh, dang, time goes fast when you're teaching. All right, let's talk. Example 2, real life problem. Volunteer to read this for me. I'll do it. Your sister is cooking her famous chili. Sounds pretty good today. When she takes it off the stove, its temperature is what? 212 degrees Fahrenheit. Okay? The room temperature is what? 75 degrees Fahrenheit. And the cooling rate of the chili is what?
Oh, 95.
0.051. How long will it take the chili to cool to the serving temperature of 95 degrees? Oh my gosh, I better get you some information here, huh? All right, here's the deal. Anybody know Newton's law of cooling? No?
Like if you put stuff over a larger surface area, then it cools faster.
All right. I'm going to give you Newton's law of cooling. All right, is that fair? Okay, here's Newton's law of cooling. You need to know this. I don't even know it. All right, but I'm going to write it down for you. It says, how long will it take to cool the chili to a serving temperature of what, kids? Okay. It says an important application of exponential equations is what's known as Newton's law of cooling. All right, so I'm going to write this down. This is about Newton's law of cooling. All right. Newton was a pretty smart guy. This law states that for a cooling substance with initial temperature T of O, the temperature T is equal to T of O minus T of R e to the negative RT plus T of R. where T of R is the surrounding temperature and R is the cooling rate of the substance. So here's the deal. T of O, that's an initial temperature. T of R is a surrounding temperature. And little r is equal to your cooling rate. I'll give you some time to write that down. Okay, let me know when you have all that stuff down. Your sister is cooking her famous chili. When she takes it off the stove, its temperature initially is how many degrees?
What's the thing next to the negative R?
It says negative r times little t. Negative RT. So t, that little t is going to represent time, okay? And that's what we're after, okay? And I'll show you that in the equation we're about to fill some parameters in for, okay? All right, kids. What does T of O represent, kids? Okay, that's the temperature when it comes up. How hot is that right off the stove? Well, what's it say, kids? What's the initial temperature? 212. So we know T of O is going to be what value here? 212. The room temperature is what?
75.
That T of capital R is like temperature of your surrounding room. So 75. T of R is going to be what value? Okay, and then little r. What's little r going to equal?
0.05.
We want to know how long it's going to take to get to a temperature T of how much? Okay, so let's fill in our parameters. What are we plugging in for capital T, the temperature I'm trying to get to? We want to cool it down to how many degrees?
95.
95 degrees. Okay, that's going to equal my initial temperature. What's the initial temperature when the chili came right off the stove? T of O. 212. Minus the temperature of the room.
75.
Okay, then this is e to the negative. All right, help me out, kids. What's the little r value going to be?
0.051.
So negative 0.051. There's a negative up there. Times which variable, kids? Little t up here. That little t represents the amount of time we're trying to get down. So when I pull it off, I'm in a room. The room's 75 degrees. The chili's 212 degrees. How long is it going to take for that chili when I pull it off the stove to get down to 95 degrees or serving temperature? Don't forget, we have to add in at the very end plus what? Plus the room temperature, which was what?
75.
Okay, 75. Mr. Gassman would be happy today. Okay? What do we have to solve for up there, kids?
Time.
Small t. Okay. Imagine this. The chili's coming off the stove. How many degrees? 212 degrees. Okay. It's in a room after I take it off the stove of 75 degrees. My question is, how long does the chili have to sit there before it's a serving temperature of 95 degrees, given that their cooling rate is 0.051? Well, here's how this works. First of all, something should jump out at you. What base are we going to be working with here? E. And when we're working with base E, and we know that logarithms apply to exponentials, what logarithm are we probably going to apply when we're dealing with base E? Natural log should jump out at you. Okay, here's how this works. Let's simplify some stuff. Help me out, kids. I need your help. How about the 212 minus 75 part first? What is that? How much?
137.
So this becomes 137 e to the negative 0.051 t plus 75. Okay. Guys, if I was trying to get everything with the exponent all by itself, what do you think your next step would be in this?
Subtract 75.
Subtract the 75. So what are you going to get on the left now, kids? What are you going to have on the left side now? 20 equals 137 e to the what? Okay. We're getting closer. Any guesses on what your next step is? Divide by. Okay, so you're saying divide by 137? I like it. I like it. I'm going to make some room here. Give me a second, okay? So what are you dividing by there, Miss Maddie?
137.
Divide by 137. Let's do it. I'll do the right side. You do the left.
0.14.
0.145. All right, kids, listen carefully on this. We had rules earlier in the chapter which stated this, and I know we had 10 straight days off, but hear me out on this. Okay, look at this right here, guys. When I have log base 10 of 10 to the first, if a base and a base match right here, what's this log base 10 kind of do to the 10? Leaving you with what value? If I have natural log, which the base and the natural log is really what, kids? E. If I have the natural log of E to something right here, what's the natural log kind of do to E right here? Leaving you with just what? Okay, so here's where we're getting at. This is the point I'm getting at. I'm going to leave you with this today. This will be the last example we have, and there won't be an assignment, all right? I'm going to leave you with this. Here's your next step. Since I'm dealing with base E and I'm trying to get this exponent out of here, we're going to take which log? Okay, natural log. So we're going to go natural log 0.145 equals the natural log of e to the negative 0.051 t. Hang in there. This is cliffhanger right now. This is getting exciting. Because on the left-hand side, can you punch in natural log of 0.145? You could, couldn't you? What is the natural log of 0.145?
Negative 1.93.
Negative 1.93. Guys, we just talked about up here. What's the natural log and the e going to kind of do to each other? If I have a natural log base e of e to some power, these cancel, leaving you with just that exponent, which is equal to negative 0.051 t. Guys, how many minutes is it going to take for that chili to get down to that 95-degree serving temp? What's your last step to solve for that little t there to find that time? So negative 1.93 divided by negative 0.051. What's that get you? About 38 minutes. It's going to take 38 minutes for that chili to be served. Holy smokes, kids. Welcome back. 38 minutes. Okay? 38 minutes. How about this, kids? The 5.4 stuff that we looked at. Take the weekend, whether it's on the practice or on the online page, polish that up over the weekend and have that stuff ready to turn in by Monday. Is that fair?
Yeah.
And then when we come back on Monday, we'll finish this stuff and get moving in the right direction again? Is that a fair deal? Okay. Do you guys have any questions about anything? Again, I'll remind you two things. Number one, check JMC, see what you have missing, because that's completely up to date. Two, that quiz that we took, if you're not happy, let's push that off to Friday as a deadline for corrections, and let's have you thinking about corrections with the understanding that if you need to come in during wind time to get help, I'm here for you. Okay? You guys good with that? I missed my second hour minions.
Will you check and see if I'm on your list?
I can do that quickly.